Good day to our lecturer, Encik Rosli bin Asmawi, and to all my fellow friends. Today, our group consisting of myself, Ahmad Danish, along with my team members, Abang Muhammad Hafizal, Nur Hazim Fikri, Albin Jimbai, and Wat Nupfil Hadi. Today, we will be presenting our project for the course PDA 10903, Solid Mechanic 1. The title of our project is Stress Analysis of a Lifting Eye Bolt and Shackle Pin Assembly, specifically focusing on its practical application in a workshop overhead hoist. Moving on to our second slide, on the left side of the screen, you can see the technical assembly diagram for our lifting system. The setup utilized an M20 thread made of 8.8 grade steel mounted through a mild steel beam. The system is subjected to a strict static load constraint of 5 kN, which is approximately 510 kg, and a 5-1 safety factor is designated for the shackle component. To ensure the integrity and the safety of this design, we establish 5 objectives systematic. First, we will construct a valid free body diagram of the entire assembly, the precise engineering to clearly isolate the forces. Next, we will formulate the equation for normal, shear and bearing stress. Third, we will calculate the actual stress generated by the 5 kN load and test them against the mild steel allowable. Fourth, we will determine the actual factor of safety to definitively judge whether this engineering design is safe for operations. Lastly, we utilize AI as a supporting analytical tool, but critically verified every output manually through an AI logbook to ensure 99.9% data integrity. Now, let's dive into the theoretical framework, which we like to call the stress trinity. To analyze potential failure points, we evaluate 3 primary types of mechanical stress. The first one is normal stress. This applies to axially load members, which in our case is the bolt shank. Next one, average shear stress, which is this focus on pins, bolts and rivets, specifically our shackle pin. The shear force cuts directly across the material. We will evaluate whether it acts in single or double shear, as this dictates to the shear area. The third one is bearing stress. This occurs at the contact surface between the pin and the eye interface. The stress is evaluated using the projected rectangular area, which is the diameter times thickness, rather than the actual curved contact surface. This foundational framework is what guides our calculations and safety factor verifications in the upcoming slides. Thank you.
Problem definition and system constraint. Bolt shank diameter D1 12 mm, pin diameter D2 10 mm, eye thickness D equals to 6 mm, eye thickness D2 equals to 10 mm. Constraint is a system under a static vertical 5 kN load. No swing, no impact. Shackle design places the pin in a strict double shear. Material specification mild steel AISI 10020. For the tension, the value is 250 megapascal, the shear 145 megapascal, and allowable bearing 375 megapascal. Our target constraint is minimum required factor of safety is more than 3.0. For the mathematical modeling, equilibrium translation, the FED and equilibrium. Total Fy equals to 0. So R minus Y equals to 0, meaning R is equals to Y. So P is 5 kilonewton. Because the eye plate sits completely between two prongs, those two jaw of the shackle, the internal reaction forces cut the pin on two distinct plates, confirming double shear geometry.
Assalamualaikum and hi, my name is Abang Muhammad Hafizal bin Abang Norini. My matrix number is CD250001. Next, let's look at the mat. To make sure this lifting assembly holds up, we evaluate three key types of stress: tensile, shear, and bearing. First, we have tensile stress pulling on the bolt shank. As you can see in the top diagram, that shank has 12 diameter. We use the standard stress formula here, sigma equal P over A shank, where P is our load and A is the cross-sectional area. That area is just calculated using the standard circle formula, pi times d1 square over 4, based on our 12 dimension. Second is the shear stress, trying to slice through the shackle pin. The pin has 10 diameter. Our formula is tau equal P over 2 times A pin. Notice that 2 highlighted in the bottom of the fraction. That 2 is there because the pin is in the double shear. The load is played across two different fellow plane where the shackle grip the pin. Finally, we look at bearing stress right at the contact point between the pin and the eyes. The diagram shows a 6 thick plate resting on the 10 pin. The formula is sigma B equal P over A bearing, where A bearing equal D 2 times D. When calculating this, remember that we use the projected rectangular area, essentially. The flat contact patch, not the curve of the hole. Now that we have the formula down, let's look at how the actual number play out under our load. Next, we apply a standard design load of 5000 newtons, and here are the raw stress result. On the left, our normal tensile stress is calculated as sigma equal 5000 newton divided by 130.1 times 10 to the negative 6 meter square. That gives us a final output of 44.21 MPa, which is well within safe limits for standard structural bolts. In the middle, the average shear stress on the pin is figured as tau equal 5000 newtons divided by 2 times 78.54 times 10 to the negative 6 meter square. This brings the shear stress out to 31.83 MPa. It's relatively low because the double shear setup we just talked about does a great job of sharing the load. But the most important number is on the right, the bearing stress. Here our formula is sigma B equal 5000 Newton divided by 0.010 meters times 0.006 meters. Because that contact area is so small, the stress jump up significantly to 83.33 MPa. The good news is that our manual math matched the system physics perfectly. But the clear takeaway here is that the bearing stress gives us our highest localized pressure. Everything is safe, but that 83.33 MPa hotspot is exactly where we need to focus when choosing material and tracking weight over time.
Assalamualaikum warahmatullahi wabarakatuh. My name is Wan Lutfi Hadi bin Wali. Trip number CD250166. Okay, moving on to our safety validation. Let's take a look at the factor of safety analysis for the assembly. On the table synthesis metric, first tension, we can see that the calculated stress came in at 44.21 megapascal and allowable limit at 250 megapascal. So that gives us a highly comfortable factor of safety is of 5.66. Next is shear. We recorded a calculated stress of 31.83 megapascal, resulting also allowable limit at 145 megapascal, and resulting of factor of safety is 4.56. Last, for bearing, exceeding the highest calculated stress at 83.33 megapascal against a 375 megapascal allowable limit. That also resulting a factor of safety at 4.5. Uh, what the table tell us that all the mode firmly in the safe zone. The bearing region is our critical failure mode. At its whole, the lowest factor of safety at 4.5. In summary, the design is robust, fully compliant with our safety margins, and ready for the next phase on. Next, for the discussion, engineering context and boundaries, boundary assumption and challenge. Dynamic variety versus static met. Assume perfectly static vertical load, real hoist, experience, impact or dynamic loads requiring a dynamic factor in 1.5 to 2.0 in physical deployment. Geometric pitfall. A common analytical trap is using the curve internal area for bearing stress instead of the correct projected area. Next, stress concentration. The MET model average stress ignore localized stress concentration around the eye, put a factor address in a solid mechanic too. Um, Broader mechanical application. The stress trinity framework is universal. The exact same analysis strategies applies to um, bolted flange joint managing fluid pressure in piping to riveted gusset plates transferring structure loads in truss bridge down to the heavy duty clevis pins pivoting, pivoting excavator booms under immense force. Mastering these three stress ensure reliability no matter the scale.
So for the AI integration and critical verification, starting from AI output, the probe AI for a sanity check, AI correctly calculate the raw stress. So the AI output error becoming from AI report bearing FOS equals to 3.0, erroneously using standard tension yield at 250 megapascal as the bearing limit. And from AI output, it comes to engineering flag. Also, human review flag 250 megapascal as overly conservative for bearing stress, which is a confined compressive contact. Others also, the source verification cross-reference again buku solid 1 PDF and standard AISC practices. We also decide, despite of checking with AI, we also finding reference for this project. So after we find some the error from AI and searching for the source, we also overrode the AI logic and we correct the official bearing FOS to 4.5 for the final engineering report. As for the final conclusion, starting from mathematical integrity, we successfully construct a FBD and map the theoretical stress trinity, that is normal, shear, and bearing, onto the physical geometry of a worship voice. Despite we also definitive safety. A 5 kilonewton load generate a maximum stress of 33.33 megapascal with all the factor of safety value exceeding 4.5. The design is unequivocally safe against the 3.0 required standard. As for the last one, we demonstrate that a single applied load generates three vastly different stresses, depending entire on resisting area geometry. Human engineering judgment remains critical when interpreting AIS's structural and analysis. As for the reference, we, we using the buku solid 1 and buku solid 2 to make us finding the core text for stress formula and theoretical framework. Despite we also using the Hebrew RC with engineering mechanics of material, 10th edition. We also using the American Institute of Steel Quotation AISC as our reference for bearing stress allowable limits. I think That's all from us. Thank you.